Okay, so we're asked to graph these. All three of these are going to form lines, so that makes it a little bit simpler for us. Number one here is already in that form of y equals, so we can just go straight to the graph. Where is that one going to start on the graph? -3, very good. Remember, there are two pieces of information given in these equations. One piece of information multiplies the x. That's the slope. That's what we do after we find a starting point. The other piece of information is either added or subtracted. That is the y-intercept. That's where we start. That tells us how far we go up or down from the origin, from the center, to start our line. So that's -3, we go down 3, we start right there, -3. That's the first point on our line. Where do we go from there? The slope of 2/3 is the top number, the 2 is a rise, the bottom number is a run. So from this point, we go up 2, we rise 2, then we run 3, so that's over 3. And that right there is a second point on our line. So our line goes through those 2 points. The second one here is also in y equals form. The order on the other side switched around a little bit, but it still works the same. Where are we going to start? At 2. So we go up 2, right there is where that one starts. Now the slope here is -3/4. Remember, the negative always goes with the rise. So from this point, we are going to rise -3. It's going to be down 3 because it's -3/4. So down 3 and then over 4. So there is the second point on that line. So that line goes through those 2 points. And again, I can get rid of that. So that's the first two. Number 3 is a little tricky. That is not in y equals form. So we have to rearrange that. We have to solve that one for y here. So we need to get y by itself, which means we have to get rid of the 5 and the 2x. Well, just like any other equation, we look at how it was built, how it was put together, and we solve it going backwards. So here, y, to build this, y was multiplied by 5 first, and then the 2x was added to it. So to take it apart, we go backwards. We're going to subtract the 2x. That was the last thing was done was adding 2x. So we subtract the 2x first. So that's gone. We're left with 5y equals 10 minus 2x is just 10 minus 2x. And then to get 5 by itself, we will, so the y by itself, we divide by 5. Remember, when we multiply or divide, we have to do it to every digit on both sides. So on the left side, it cancels out the 5, leaving us with y. On the right side, we do 10 divided by 5, which is 2, but we also have to do -2x divided by 5, which is a -2/5x. Where do we start on that one? At 2, right there. +2. And from there, we will go down 2/5. Remember, we said the negative goes with the rise. The rise is either up for positive, down for negative. The run is always positive, always goes left to right. So there's our lines on the graph. Any questions on those? Any questions on the homework from last Thursday? Okay, so you may have noticed our lectures were getting slightly ahead of the homework. That is intentional because I want to give us a little bit of time on Thursday to review. My hope is to finish up all the material in the first 45 minutes or so on Thursday to give us at least a good solid hour to review for the test coming up. Just because there's kind of a couple of topics thrown in here. I mean, it's mostly geometry, but with areas and volumes are very different from this graphing. So we finished up last time with data graphs, the circle graphs, bar graphs, and all that. That's kind of a transition from this geometric graphing into handling data and statistics. So the last little piece that we have to deal with here is statistics. So what we're going to look at today is we're going to look at the more formal side of statistics of how do we summarize data. Now in the next 3 hours or so that we're going to have to deal with this, obviously I'm not going to get very deep into statistics. Statistics is a topic that's very difficult to squeeze into a 1-semester course, much less a few hour, a couple of 1-hour lessons. So we're just going to touch on the surface. But to talk about statistics, there's some vocabulary that you need to know about. The first thing is a population. A population is the group that you want to learn about. It could be people, it could be parts on the assembly line, any group of things that you want to learn about. A parameter describes the population. A popular statistical example is always elections. So let's say that we have an election coming up, and a week before the election, we want to try to predict who's going to win. What is the population we really want to learn about there? Is it the candidates? No, because they don't really determine who wins. Who determines who wins? The voters, right? So the population we really want to know about there are the people who are going to vote in that election. It's not all registered voters, because not all registered voters are going to vote. We only care about the people who are going to vote. Well, as you look at that example, that population, that's hard to define, because a week before the election, there might be people that don't know if they're going to vote yet. So they don't know if they're in the population or not. That's one of the reasons why we most often use a sample. A sample is a smaller group or a subgroup of the population. And there's a lot of reasons why we would take a sample rather than looking at the whole population. One is what we just said, is the population can be hard to define. Might not be totally sure who is in and who isn't in the population. Of course, the next two are always the big ones: time and money. There are roughly 320,000 people in the United States. Of them, about 180,000 are registered voters. Or sorry, 220 million people. About 180 million of them are registered voters. Would we have time to survey 180 million people? No. So obviously the time would not fit, and the cost, the money, would not be good. Also, I'm just going to call it elapsed time during the process. What I mean by that, let's say that, okay, we decide that we're going to do 1,000,000 people. Well, even that might not be practical because it might take 3 or 4 days to contact that many people. But what happens if on day 2, one of the candidates says something really offensive or stupid? Well, that might change the opinions of people and who they're going to vote for. Some of the people you've already surveyed may change their mind and be voting for somebody else. So the conditions have changed and you're not done with it. Part of any statistical process is keeping the conditions constant during the process. And the longer it takes, the more likely it is that conditions are going to change. So that's a problem. Now the last one, there are a lot of other reasons. The last one I'm going to list hopefully doesn't apply to surveys. It's more of a manufacturing thing. It's destructive testing. Let's say you work for a company that produces parts, and those parts need to be able to hold a certain amount of weight when they're being used. They need to take a certain amount of force. But your quality control person is going to take one of those parts, put it in a tester, and that tester is going to stretch it until it breaks. And it's going to measure how much force it took to break it. And if that force is large enough, they'll say, okay, this part's good. Well, why would we not want to test every part? Well, because once we test it, the part is broken, right? We can't test every part or there'd be nothing left to sell. So we have to take a sample. We test enough of the parts that we're relatively confident that the rest of the parts are good too. Like I said, there's a lot of other reasons why you would do a sample. Those are just some of the main ones. Well, a statistic is a piece of information that describes a sample. So let's go back to our election example again. And let's say that 112 out of 200 surveyed favor candidate A. That is a statistic. Because that describes our sample. We sampled 200 people, 112 of them say they'll go for candidate A. Now, parameters, we don't usually know. Now, in an election case, after the election, we know, but at that point in time, 1 week before the election, we don't know what that parameter is. So the purpose of taking samples and finding statistics is to try to estimate the parameter. If we know the parameter, like I said, there's absolutely no reason why you would take a sample and calculate statistics off of it. So what we might state is we estimate about 56% of voters favor candidate A. That came from that sample statistic, but it is a parameter because it is a statement made about the population. It may not necessarily be completely accurate, but it is an estimate of a parameter. It's a statement about the population. For this to all be good, we have to have what's called a representative sample. What that means is the properties of the sample are the same or very, very similar to properties of the population. So in this case, the percent that favor A in the sample better be approximately equal to the percent that favor A in the population. Doesn't have to be perfect, but it better be close. In this last presidential election, for example, there were several surveys done that showed Clinton at like 52% of the vote and Trump at like 41% of the vote. But many of those, when the actual votes were in, were much different. That was an example of not taking a representative sample. To do a representative sample, there are two considerations: sample size. Bigger is usually better. The more people you sample, the more likely you are to get accurate numbers. If I wanted to know how students in WITC, who they were going to vote for, if I went out in the hallway and I asked two students, one said candidate A, the other said candidate B, could I conclude that 50% of the students favor candidate A? No, that's too small of a sample. It's not big enough. The other is it has to be random. Random means every member of the population has an equal chance of being in the sample, of being selected. So by going out in the hallway here, I'm not random either, because people from other campuses have no chance of being selected. In fact, people from Rice Lake that aren't on campus on Tuesday evenings don't have any chance of being selected. So it has to be a random sample. If this were a formal statistics class, I would talk a lot more about how big does the sample need to be, what are ways of selecting a sample to make it random. Believe it or not, there's random and then there's more random. It's called simple random. We're not going to get into that here. I want to move on to organizing data. As we mentioned last week, when we take statistics, there is a question being asked. And it's the answer to that question that is our random variable. And we had mentioned that random variable, that answer, could put you into a category. Could be like favorite color. What's your favorite color? That puts you into a category. That's a categorical variable. Or it could be, that answer could be a number. If you ask, what's your height? That's a number. How many classes are you taking? That's a number. That makes it a numerical variable. Numbers, numerical variables, are split into discrete and continuous. Discrete are things that are counted. How many classes do you have? How many cars do you own? How many children do you have? Those are all discrete because they're counted. Continuous is measured. How tall are you? How much time does this take? Those are all things that are measured. One of the technical definitions of discrete is no matter how close together two numbers are, you can always find a number in between them. No matter how close together two times are, there's room for a time to be in between them. And we looked last week at those graphs, organizing the data into tables and making graphs, bar graphs, circle graphs, and so on. So we can organize data with tables and graphs. And remember, there were strengths. The tables, the big strength of the table was it gave us exact numbers. The big strength of the graph is it gave us quick comparisons. By quick comparisons, I mean largest, smallest. Which is bigger? And so on. Well, today we're going to look at summarizing data numerically. And to summarize data numerically, we need to understand something called a data distribution. The simplest representation of a data distribution is called a dot plot. You don't need to know the term. What a dot plot is simply a number line. I'm going to make that actually somewhat look flat. Hopefully that's a little bit better. Let's say on the last test, let's say scores ranged from 60 up to 95. And so what I'm going to do is I'm going to represent those scores on this plot with a dot above where that score was. So let's plot the scores. Let's say that I had the first test graded was an 82, so I put a dot there above the 82. The next test maybe was a 91, I'll put a dot at 91. Then maybe an 84 and a 76. If I had another 82, I put that dot above the previous dot. Well, now this class only has like 21 people in it right now. But let's say I take all my test scores on that test for the last 8 years, and I plot them on this graph. And as those dots stack up, we'll see that it forms kind of a pattern, a shape. And that shape is called a data distribution. If I trace the top dots above each number, I get that shape. There's kind of a bell curve. You guys have probably heard that term of a bell curve before. The technical name for it is a normal distribution. Well, if I wanted to describe that curve, one of the things I might say is that the center of that curve is at about at 81. Let's say I have another curve that looks like this. If I wanted to describe that curve, I would say that its center is at about 78. So the difference between the red curve and the brown curve is the location of their center. Well, let's put another curve up there. This purple curve has a center that's still at 81. So the red curve and the purple curve have the same center. How would we describe the difference between them? Well, the purple curve is narrower, thinner, however you want to describe it, right? That is less spread out. So the two things that we use to summarize these curves is the center and the spread. The center literally describes what number on this number line that the center of the curve is above. The spread describes how wide the curve is. Now, there are several different ways of describing center and spread. So let's look at measures of center here first. And to work on this, we're going to put a set of numbers over here. In fact, I'm going to change this just ever so slightly. We'll let that be. That'll work. So I've got 5 numbers over there. First thing I'm going to define, n is the number of items in a list. So for this list down here, n equals what? How many items are in that list? 5. So n equals 5. Our first measure of center is one that you've all probably used before, but maybe you haven't heard it called this. It's called the mean. And the mean is just what most of us have called the average. You add them up and you divide by how many are there. The symbol for that is the sum. That funny looking E thing is called the sum, which means add them all up. X just stands for each of the values. So you add up each of the values and you divide by n, which is how many are there. So this would be calculated by doing 7 plus 13 is 20, plus 19 is 39, plus 11 is 50, plus 14 is 64, divided by 5, which is going to be 12.8 is our mean. Any questions on how we found the mean? Second is the median. Well, when you're driving down the highway, where do you find the median? It's in the middle. So to find the median, it's a little bit more of a process. There's 3 steps. Step 1 is you put the numbers in order from smallest to largest. So I'm going to do that here quick. That'd be 7, 11, 13, 14, and 19. Step 2, find the position of the median. Now, many of you might have been taught for small sets like this, you just cross off the first and last, cross off the first and last, and you see what's left in the middle. And for small sets, that does work. As they get bigger, that's not such a handy way of doing things. The position of the median is just 0.5 times n. So for this, that'll be 0.5 times 5, which is 2.5. Since that is a decimal, we would round up. 2.5 rounds up to 3. So that says the third number is our median. So the third step is find the median. So that just means we go up here. The third number is 13. So the median of that list is 13. Notice that's pretty close to the 12.8 we had for the mean. In a good set of data, the mean and the median should be either the same or really, really close. Now you'll notice when we did that, we said this came out to a decimal, 0.5, so we round up. Well, what if that didn't come out to a decimal? What if I had a different set of numbers? Now I'm going to put them in order from the beginning just to make it easier. So let's say I have the numbers 5, 11, 14, 15, 17, 19, 22, and 31. There are 1, 2, 3, 4, 5, 6, 7, 8 numbers in that list. So in other words, n equals 8. So my position here is 0.5 times 8, which comes up to be a 4. Since that is a whole number, that means the position is between that location, which is the 4th, and the next location, which would be the 5th number. So it's between the 4th and 5th number. So in this case, that's between 15 and 17. How do I find what's between them? I add the two together and I divide by 2. Now, when you do this on your calculator, when you add these together, make sure you hit equals after you add before you divide by 2. Otherwise, it's going to give you something like 23.5. Well, 23.5 is not between 15 and 17. What it does is division order of operations, it divides before it adds. So if you don't hit equals after the 17, it divides the 17 by 2 and then adds it to the 15. So you have to hit equals. 15 plus 17 is 32, divided by 2 is 16. So the median of that set would be 16. If you were crossing off the smallest and largest, you would end up, you'd get down, there'd be 2 numbers in the middle, so you'd do the same thing. You'd add them together and divide by 2. The third measure of center is something called the median. Just talked about that one. Called the mode. The mode is the number that occurs most often. Now you'll notice in both of the data sets I've given you so far, there haven't been any numbers repeated. So in those data sets, there was no mode. Now there might be data sets where there's several numbers that are repeated twice or 3 times or whatever. Some texts, but there's different fields of thought on that. Some say that you can have one mode or there isn't one. Others say you can have up to 2 modes. If there's more than 2 numbers that are repeated that same number of times, then there's no mode. Other textbooks are going to really elaborate formulas of the square root of n, whatever is how many modes you can have. For this class, there's 1 or none. So if it isn't just a single number that's the mode, then there is no mode. If there's 2 different numbers that are repeated twice, that would be no mode for our purpose. The mode is most useful for categorical data. Categorical data, you can't calculate a mean or a median because there's no numerical values to put in order or to add together. It's like the favorite color. You would have the mode would be the color that was chose the most often. So categorical data really is the best use for mode. Another measure of center, the final one that we're going to talk about, is something called the mid-range. The mid-range involves taking the largest number, the maximum, plus the smallest number, the minimum, and you're averaging together. You're adding them together and dividing by 2. So for our original data set up here, our smallest number was the 7, our largest number was 19. So our mid-range, maximum 19 plus minimum of 7 divided by 2. Again, make sure you hit equals when you add those together. That'll be 26 divided by 2, which is 13. Notice that's really close to our median and our mean as well. It's actually the same as our median. It's really close to our mean. You've probably already figured out my opinion of the mode as a use of measure of center. Like I said, it's really only good for the categorical data. The mid-range is very quick, but it can be unreliable, especially if you have some extremely small or extremely large values. So it comes down to the mean or the median. Which is best? If I took a vote in here, show of hands, how many of you would say that the mean is the better measure of center? Okay, nobody? One? Okay. How many would say that the median is the best measure of center? 2, 3, 4. I've got 1 and 4. How many don't care? Those hands go up. Okay, usually I get quite a few people that vote for the mean, and for a couple of reasons. One is that's the one we've learned probably around 3rd or 4th grade. We learned how to average numbers, and that's what the mean is. Also, it feels very satisfying. You crank it into a formula, add them up, and you divide. The median feels a little more wishy-washy. You have to put them in order and find the middle one and all that. But I'm going to give you an example here. In 1983, University of Virginia published that the average starting salary for a graduate in their bachelor's of marketing program. Do we have any students here that plan on going into the marketing program? A couple? Okay. Well, then this will be really interesting to you. The average starting salary for one of the graduates in 1983 in their bachelor's of marketing program was just over $78,000 per year. Now, that would be a phenomenal starting salary right now. In fact, I'd be enrolled in the marketing program. Think about 1983. In 1983, your average high school teacher was starting out between $16,000 and $17,000 a year. That's a lot of money. Well, what they failed to disclose. One of the graduates that year was a man by the name of Ralph Sampson. And looking around the room, there's probably none of you that are old enough to remember Mr. Sampson. Mr. Sampson was 7 feet 4 inches tall, played on the University of Virginia basketball team, and was the two-time, both his junior and senior year, NCAA Basketball Player of the Year. He was drafted first overall, number 1 draft choice to the Houston Rockets. How much do you think he made that year? A little bit more than $78,000. He signed a multi-million-dollar contract. I don't remember the actual number, but it was like $6 or $7 million. It takes a lot of $20,000 a year marketing graduates to average out a multi-million-dollar contract to $78,000 a year. This was a mean. The median, you guys ready for this? The median was $24,000 a year. In fact, Mr. Sampson was the only one who made over $33,000 in that group. It's something called stability. The median is more stable than the mean. In a good set of data with no extreme values, the mean and the median should be about the same number. So there really is no real reason to worry about it. Apparently my ink is not stable tonight. Let's take a peek here. Let's take a set of numbers here. 11, 15, 18, 21, and 30. I put them in order for a reason. Let's find the mean of those numbers. I'm going to have you do that quick in your calculator. Find the mean. You guys get a mean of 19. What would the median be? Well, I just cross off the first and last, the middle number is 18, right? So the mean is 19, the median is 18. Let's change this a little bit. Let's do the same 5 numbers, but I'm going to put 73 on there now. So there's 6 numbers. Find the mean of that. What do we get? Is it 28 now? 27.6? The median, cross off the first and last. First and last, we have 2 numbers in the middle. Oh, I know why. That should have been an 18, not a 16. I just wrote it wrong. But either way, 2 numbers in the middle. That would be 28 if I had the number right. Between 18 and 21, that's 39 divided by 2. You get 19.5. So you'll notice here, by adding that one number, that 73, which is way larger than the others, the mean went from 19 to 28. The median only went from 18 to 19.5. So the median is more stable because it's not affected as much by those extreme values. Okay, we're a minute early for break, but let's go ahead and take our break. It is 4:19. Let's come back at 4:29. So let's roll. So now we're going to look at measures of spread. Sometimes referred to as measures of dispersion, how the numbers are dispersed. So I'm going to look at a set of numbers here, and I am going to put them in order from smallest to largest. Let's do 7, 14, 15, 17, and 22. One of our measures of spread, the first measure of spread we're going to talk about is the range. Now we have the mid-range up above for a measure of center. The range is very closely related to that. It is just the maximum minus the minimum. In other words, the largest number minus the smallest number. Well, over here, the largest number is 22, smallest number is 7. That gives us a range of 15. Now, we can come up with a second set of numbers. Let's do 7. Let's do 7, 8, 15, 21, and 22. Is that going to work out? No, it's not. Let's do 7, 9, 15, 21, and 22 should work out a little bit better. As I look at those numbers, would you say that those are equally spread out? I'd say probably not, right? But the range, the largest number is still 22 and the smallest number is still 7. The range is still going to be 15. So the range is not capable of distinguishing between those two sets of numbers. I can compare them using a dot plot. Maybe. Where I put this, do the top set of numbers in green here. So I've got a 7, 14, 15, 17, and 22. And we'll do the bottom set of numbers in purple. We've got a 7, 9, 15, 21, and 22. It's pretty obvious to me that the purple numbers are more spread out than the green numbers are. So there's a measure that's more precise than the range, and that is called the standard deviation. Yep, I realize I just... So the standard deviation is often combined with the variance. And it's a 6-step process. The formula for it is extremely ugly. So I'm just going to give you the steps. So it is 6 steps. So brace yourself. Step 1, and we're going to use the green set of numbers up here, is to find the mean. So the mean of that set of numbers, 7 plus 14 is 21, plus 15 is 36, plus 17 is 53, plus 22 is 75. Divided by 5 gives us a mean of 15. So that's step 1. Found the mean. Step 2, is to subtract the mean from each number. So 7, 14, 15, 17, 22. So I'm going to subtract 15. What's 7 minus 15? Negative 8. 14 minus 15? Negative 1. 15 minus 15 is 0. What's 17 minus 15? It's 2. And 22 minus 15 is 7. What we just found there, that set of numbers is referred to as the deviations, or often the deviations from the mean. If you wanted to double check your calculation at this point, by the way, those should always add up to 0. Step 3 is to square the deviations. So what is negative 8 squared? Now when you punch this in your calculator, be very careful. If I just do negative 8 and squared, it's going to try to tell me it's negative 64. What's wrong with that? It's negative. Any number squared should be positive. When you put that in your calculator, negative numbers have to go in parentheses and then squared. Give us a positive 64. So yes, negative 8 squared is a positive 64. What's negative 1 squared? 1. What's 0 squared? What's 0 times 0? 0. How about 2 squared? 4. And 7 squared? 49. This set of numbers here, by the way, is referred to as the squared deviations. Step 4. Is to find the sum of those numbers. So I'm going to add them up. It is going to be, what is that, 113? Does that look right? No, 118. That is referred to as the sum of the squared deviations. Creative name, right? Step 5 is the tough one. Step 5, you're going to divide by n minus 1. For this data set, n equals what? How many? How many numbers were in this list? 5. So n equals 5. So that means n minus 1 equals 4. You divide by 4. What's that, 29.5? Is that what we get? That number there, the result of step 5, is called the variance. When we do some statistical testing, there are certain statistical tests that use the variance instead of the standard deviation. Our standard deviation does come up here now, the result of step 6. That's to take the square root of that step 5, square root of the variance. Square root of 29.5 is going to be 5.43. That's not a process we want to repeat a whole lot. We will review finding standard deviation at the beginning of class on Thursday. There are some things that I want to talk about that fit in with that standard deviation and what we've calculated so far with our mean and median. There's something called the empirical rule. The empirical rule involves that bell curve again. That doesn't even look half bad. A little tipped, but it's okay. The center of that bell curve, of course, is our mean or our median. We're going to use the mean. And it's pretty clear how the center, the mean or the median describe the center. It's just right in the middle of that curve. You fold it in half, you'd be folding it around the mean or the median. The spread of it, how the standard deviation describes the spread, is a little bit trickier to do. And what we're going to do is we're going to use something called the approximate empirical rule. There's something called the exact empirical rule, which uses exact numbers. But we'll review this again more on Thursday as well. But what it says is 34% of the data is always found on either side of the mean, between the mean and 1 standard deviation away. So this would be minus 1 standard deviation, 1 standard deviation below the mean. This would be plus 1 standard deviation, or 1 standard deviation above the mean. Next, between that location and the next spot, 2 standard deviations below the mean, is 13.5% of the data. On either side. And then between there and the next step is 2.35%. So that's minus 2 standard deviations, or minus 3 standard deviations, to plus 3 standard deviations. And outside of that range is 0.15% on each end. These percents are constants. What changes are the mean and the standard deviation for the data set. Let me give you a for example. Let's say you are going to buy a home and you want to purchase a 3-bedroom, 2-bathroom home. And you do your research. And You look at the area where you want to buy this home, and you look up over the last several years, the average, the mean selling price of a 3-bedroom, 2-bathroom home is $120,000 with a standard deviation of $25,000. So what that means is on this bell curve, the center number here is the mean. That's 120,000. I'm just going to write 120 there. One standard deviation below the mean, well, I would take the mean of 120,000 and I would subtract the standard deviation of 25,000, which would be 95,000. Again, I'm just going to write 95. The next step down, I would subtract the standard deviation again. What is 95 minus 25? That'd be 70,000. Another step down would be minus another 25. That'd be 45,000. Going the other way, 120 plus 25, one standard deviation above would be 145,000. I continue to go, another 25 would be 170,000. This would be 195,000. Now let's say you're looking at homes and you find one that you absolutely love. And it has a price, asking price of $170,000. And your agent is telling you, boy, you better put in an offer on this house right now. It's going to sell real fast. And you better give them their full asking price or they're not going to listen to you. They're going to just move on. Well, what this curve is telling you, 170,000 is right here. If you want to know how many houses are cheaper than that, cheaper is going in this direction. So we would add up these percents here. If you add those all up, that's 97.5%. What that is telling you is 97.5% of all 3-bedroom, 2-bathroom houses that have sold in that area in the last several years have been cheaper than $170,000. In fact, if we went the other way, more than 170 is this direction. That's only 2.5%. Only 2.5% of all 3-bedroom, 2-bathroom houses in that area have sold for 170,000 or more. So what does that tell you about your chances of finding a cheaper house? Probably pretty good, right? 97% of the houses in your specification will be cheaper than that. Again, we'll explore the empirical rule a little bit more on Thursday. The next thing I want to look at is something called z-scores. One of the weaknesses up here, this empirical rule, is, well, what if the price was 150,000? Well, that doesn't fall right on one of those standard deviations, so it's hard to do much with it. The z-scores allows us to be a little bit more comparative. And the z-score is really used more for comparing between two populations. A z-score, the z-value is equal to the number minus the mean for that population divided by standard deviation. And what it does is it standardizes that score so we can compare it to scores from other populations. For example, let's say that you have two students. We'll go student A and student B. That is the level of my creativity at this point in the evening. Student A took the ACT. And on the ACT scored a 29. Student B took the SAT. And on the SAT scored 1,430. Who had the more impressive score? Well, looking at it, it looks like it's almost impossible to tell, doesn't it? They're two different tests. But let's say that we look at the ACT. The mean score is an 18 with a standard deviation of 6. Let's say on the SAT, the mean score is 950 with a standard deviation of, well, let's go 200. Let's find the z-score. So for student A here, their z-score would be their score of 29 minus the mean of 18, then that result divided by the standard deviation of 6. 29 minus 18 is 11. Divided by 6 is 1.83. That's a positive number. What that is telling me is this person was above average. They were 1.83 standard deviations above the mean. Let's find the z-score for student B. Their number was 1,430 minus the mean of 950 divided by the standard deviation of 200. Well, we subtract 1,430 minus 950 is 480. Divided by 200 is a 2.4. That's also positive, so they were above average, above the mean, but they're 2.4 standard deviations above the mean. So what that's saying is student B's score is much more impressive than student A. So even though those are totally different tests, we can still compare them to each other basically by comparing them back to their own population. We'll review z-scores a little bit more on Thursday as well. There is a new quiz due tomorrow, Wednesday. Of course, at 11:59 p.m. again. And there's a new homework due Thursday at class. Like I said, I do realize that my lectures are actually getting a little bit ahead of the homework. Most of what we discussed tonight will not be on the homework until the homework that's actually due for next Tuesday. But I wanted to get a little bit ahead of lecture, so if anybody wants to get ahead on that homework so that they have more time to study for the test for Tuesday, you can. And also, I wanted to make sure I have plenty of time this Thursday to review for the test. So with that, if you guys want to stick around, I will be here till 5:20. Otherwise, you guys have a good night.